Welcome everybody, I'm Alfonso and I'm going to show you how to do, if Simba is a cool simulator already, I'm going to show you how to do a proper simulation for magnetics in a cool open magnetics way. So first I'm going to tell you about what we are going to do. No, we are not going to do any spoilers, sorry. So we're going to start talking a bit about open magnetics and how it started. You know that in general for magnetics design we have really cool software, but not this. Sorry, this is for semiconductors. This is the one we have for magnetics. It's a bit old, so if you take a look closely, you can see that the models, the most advanced models that we normally have, are Steinmetz or Doles. What does it mean? It means that the first model Steinmetz was made was made by a guy who was born in what today is Germany, but was before became Germany. He was a Prussian. So this is like really old model. And then the second one is Dole from the 66, and this is still the most advanced models. Most people still use DC resistance to model the winding losses. So what happened here? Like, did power electronics modeling peak in the 60s and we are just going downhill from here? The reality is not. If you analyze the modeling, you can see how the more and more advanced and more complex, but better and more accurate models are developed over time, especially in the last years with the development of technology, software, and everything. So then what happened? It happened that another thing was developed in 1986, Excel, Microsoft Excel. And this really put a stop, not a stop, I call it a threshold. This is the Excel threshold. So we are from that point, we start differentiating into models that can be implemented in Excel, because at the end of the day, it's a good tool. We engineers use it to calculate stuff. But we differentiate the models that are under the threshold as the ones that can be implemented in an Excel cell, like Steinmetz, Doles, or Partridge. And then we have the ones that are over the threshold, like the improved generalized Steinmetz or the Bean-Lorenzo that move a bit, but basically to calculate the magnetic field for rectangular wires and the leakage inductance and all that. But they are not difficult or complex. They are that you cannot just put them in a formula in Excel. So to lower that threshold or to change it, I started developing open magnetics with the target to have to decrease the cognitive load that a power engineer need to design their magnetics, because when you are working on a power converter, you have a certain amount of time and energy that wants to develop to modeling. And that's what is marked here by the Excel threshold. So if we facilitate the task of modeling magnetics, the engineers can make use of much better models, much better, more accurate models, and design better magnetics. How do we do this? First, with open source and transparency, public validation, peer review, in a sense, trust. For that, we have created a common language. We are going to talk more about that, but basically it's a standardization. Then we try to really put a lot of effort in the graphical interface to make it comfortable and usable. And so you need it has hopefully a low learning curve compared to other stuff. And then speed. Speed is important because, yeah, you can simulate something and take 5 minutes to calculate one parameter, but if it takes 5 milliseconds, you can do more stuff in that time. You can run it, you can parallelize, you can do sweeps, you can do a lot of optimizations with that. And not only that, even if when you are using it in the graphical interface, the fact that you just have to wait a bit, it keeps your attention and makes you focus and design better. So the current status, or where this fits, is that we have the industry where they always do things. They have sentences like, "This is how we do things. We don't have time for doing this properly. We'll do it in the future." And then we also have the academia, which is when you are studying, you are a PhD student, you don't have time. You just need to get your publications, and then you say, "Okay, when I am a professor, I will have time to do my stuff." But then when you are a professor, you don't have time, and then you give the stuff to the PhD students, which in turn they won't do it. So with all this, the idea of OpenMagnetics was to bring together, to create a bridge between the academia and the industry. So we take what the industry needs from the designs, and we implement the models, the automation and the customization, and we give all the data to the industry to make their work, and don't forget about the problems of modeling and magnetics. And from the academia, we get the modeling theory, we get the papers, we implement the models, and we give feedback about the accuracy, comparing it like all together, not just each paper always is the best one, but no, we put all together and we actually get the best ones. I don't know, going a bit back to the softwares that are used nowadays. I don't know how is your eyesight, but if you take a look at the materials typically used, and you know a bit about magnetics, you will realize that these materials are obsolete, and they have been obsolete for 10 years. So OpenMagnetics is not only between industry and academia, this is also for manufacturers. So we collaborate with the manufacturers and with the power associations. We exchange the data, we make sure that we have all the data from their materials. And we also integrate with other tools, with Spice, with Trafolo, with Simba, which is why we're here, with ANSYS. And to do all this, we have developed a language, like a hardware description language, to describe a magnetic, to store all information and of a magnetic in a file that you can then exchange with other softwares and other colleagues. Basically, it's also open source. It has some rules that cannot be. It's totally unambiguous. The magnetic is perfectly designed. It includes the excitations, the results of the simulation. It includes the measurements. Among other things, it has to be human readable and machine readable, because the target of all this is to create a proper database, like a proper structure, to create really artificial intelligence for power electronics, for magnetics, because we cannot have power electronics without a database and without a data set of designs and without information. So this is the foundation to that. Some examples of this language is, okay, you can have like an e-core, and this is how it is stored. Like you have all the information about that. You can also have a material. This is the 98 from Ferrite, and you can also store all the material. So you don't need actually to go to the graphs and look to the crossing point between the logarithm, the scales. No, you have all the data already in the tool. You can just get it interpolated and actually calculate the proper data from the measurements, not from the graph data. This is important. We get the data from the manufacturers because we collaborate with them. We also have an open source database with many materials, core shapes, wires, like thousands and thousands of cores that you can just buy, and they're in stock. Bobbins is also, as I said, is free, it's open source, anybody can access to it. It's updated, and then to use all these models that we have implemented, to use all these materials, database, and this file at the end, when you have a file that defines completely a magnetic, is big. So because this is not trivial to create manually, we have created what we said, a graphical tool to develop all this. This tool, the user can just pick the parts, and he will get the results, the simulation in a few seconds, can configure the wire, any type of wire, rectangular, any standard, the American, European, all the manufacturers on the core, like do interleaving, and we'll do it, we'll take a look. So now I'm not finished, but this is in the middle time. I'm going to do a demo because then I know that at the end you are all tired. So let me see. You can see the page, Manu?
Yes, Alfonso.
Yes, we can.
Good, thanks. So this is OpenMagnetics web. You don't need to register or anything. The idea is that you can create a magnetic, but first, well, I know the magnetic we're going to do. So it's a flyback, this, but then we need the waveforms, and this is what Simba comes into play. Wait, Tolly, I need to share my whole screen. Give me a moment. Can you see it? No?
Yes,
Okay.
It's perfect.
So I have prepared this is actually the flyback example that Simba brings as a reference design. So this has like a typical flyback inductor. So we just need to simulate it. This is why I put 220 microhenries. We get here, and we need to get the waveforms. Just need the input, current, and voltage for the transformer, for the inductor. So we are going to put here, sorry, this has to be CSV. And that's it. Then we come here, we import it, and we confirm the columns, and we get the waveforms from that. We can select 12 different columns, but we can also trust that this will get it properly. And that's it. We have already the requirements, the waveforms. So now we have to choose what we want. In this case, we have several options, but I want to build my own magnetic. So in here, it's a bit like the GIFs you have seen. You can select the shape family and then the core, the material, the wire, or you can just say, advise me a core. You know better. So we get an EFD, and then now we have to select the wires, and we can do the same, advise all of them. And we get the design. We can see the losses. If we go to the secondary, we can check the leakage inductance, which is not so nice because it's normally it's better for flyback. So let's do some interleaving. To interleaving, this is the order of the section. So let's put 1, 2, 1, 2. And now, because we are adding layers, probably the design won't fit. So yeah, so we need to put some smaller wires to make sure that it fits. And now, if we go to the secondary, you can see that the leakage inductance has gone to 3 microhenry, so that's much better for us. If we continue to a summary, you get the result. You can get a summary here for all the results, the permeability, all the design results, the losses, and then you can. There's a new button here. You can export it to Circuit Simulator, and we have two options. We can either download the sub-circuit directly for Simba, or we can tell it, no, I'm going to give you the simulation I already have, and you are going to return it to me with the library already inserted. This is what I did. So if now we open this, I have prepared another one, like the one before, but just with the empty magnetic space. And if now we go to libraries, now we have one library called OpenMagnetics component, and we just can add this one here. And if we take a look, we have automatically generated the magnetic circuit with Simba's new library. So that means that we have all the legs, the magnetic paths of the core, like this, because it has 3 legs, we have this. If you have a toroid, then you will have only one. With all the reluctances and the gaps, including the residual gaps, because this is important. And then you have all the windings, primary, secondary, with the AC resistance at that frequency, and with the primary leakage, actually with the whole leakage inductance. And if we simulate this, Simba does it like really fast. We can check that it really does the simulation as before. And with this, we can modify the magnetic and just reinsert it and check how using different components, like really simulated components, with their magnetic fields can affect the simulation in our designs. And this can be done for any topology, any converter, and any kind of magnetic. So let me go back to the presentation because I'm not finished, but it's little to go. So this is what I was showing you with OpenMagnetics, and with this mass format, you can create automatically from the waveforms of the circuit simulators. You can get the magnetic designs, prototypes directly. But you can also get it for finite element simulations. You can download that file and open it in ANSYS, and with a little click, we'll show you actually soon. You will get the 3D simulation completely automatically for eddy currents, transient, with the waveforms that you inserted from Simba, and also for the thermal one. This is also for ANSYS, and we're planning for more. Trafolo is also going to be here and do this, and probably the whole systems. And not only that, you can also use it with the manufacturer. So in the same way that you create with KiCad or KiCad, I don't know, there are people who say KiCad. With KiCad, you can do a PCB, design it, you export a Gerber file or an ODB++, and you send it to the manufacturer, and you get the PCB at your place. We are doing the same. So you can go to OpenMagnetics, design your magnetic, get the mass file, send it to the manufacturer, and you will get it in your at home. And actually, the idea Würth will be the first one to support this, Würth Electronic. And I think, yeah, basically we do this because this is the features for magnetics. There's no reason why it shouldn't be a commodity like PCBs. And that's it. Any questions?